Yeah. Good morning, every one of you. So, am I audible to everybody?
Yes, sir.
Yes, sir.
Thank you. Yeah. Then today we are going to start this Unit 1 in mass transfer operations. So, which is diffusion. Okay, what is the diffusion? We will be discussing more about the diffusion in this chapter. So, it will be very easy if you understand this concept. The mass transfer operations, dealing with the mass transfer operation will be very, very easy. If you don't understand this concept, entirely the mass transfer will be a completely unknowing thing for you. So try to concentrate more on this one, diffusion. So what it is taking place. So all this, the pictures, if you observe in these pictures, whatever the phenomena it is taking place here in this picture is everything is a diffusion. Whenever you are throwing some color into some water, how if it is spreading throughout this water or throughout this liquid, how it is spreading using diffusion only, it is spreading throughout this glass full of water or glass full of some liquid. Okay, in the gas phase, similarly in the gas phase, if you see, there is a gas phase and another is a subatmospheric pressure, nothing but vacuum. Okay, whenever some molecules are there at high above atmospheric pressure or in the gas phase, okay, the gas movement will be from the higher pressure region to the lower pressure region. Obviously by the normal sense, it can move from higher pressure region to lower pressure region. Here also, similarly the same in the diffusion, dialysis, osmosis. These are all the examples of our mass transfer phenomena. Okay, the concentration. Okay, the molecules will move from higher concentration region to lower concentration region. This is the phenomena everywhere. Okay, as I said you earlier, the fragrance, how we are just spraying the fragrance into the air, everything, room fresheners, whatever we are using, how after just giving the room freshener, how that fragrance we are sensing out. Okay, the good smell we are sensing out due to the diffusion of that molecules which is present in that room freshener is spreading out throughout the room, throughout your room. Then only we can smelling that one. So that is the phenomena. What is happening is called as diffusion. So what are the contents in this Unit-1? So generally I will introduce more about this, what is a diffusion. The next, the governing law for the mass transfer is this fixed law. You might have seen in the fluid mechanics, the law that is Newton's law of viscosity. Tau is directly proportional to du by dy or du by dx, whatever it may be, you have seen. Stress is directly proportional to strain, in which the proportionality constant is viscosity. You have seen in the fluid mechanics. Similarly, here also fixed first law of diffusion will be there. And similarly, in the heat transfer also, you might be seeing in the heat transfer course also, there is a Fourier's law of heat conduction. Okay, Fourier's law of heat conduction. Q is directly proportional to dt, temperature, change in temperature with respect to I think dx. Okay, change in temperature with respect to dx or dt, I don't remember exactly. So in which the proportionality constant will be your k, thermal conductivity, that is dt by dx, dt by dx or dt by dy. Okay, similarly here also fixed first law of diffusion will be there, that we will be discussing. Fixed first law of diffusion is there, fixed second law of diffusion is there. Among them, fixed first law of diffusion is very important. It is the basic governing equation for mass transfer. The next, continuity equation. So during derivation of this fixed second law of motion, we will be observing some continuity equation. So you might have seen in the fluid mechanics, m dot is equal to rho into u into s. Okay, where rho is a density, u is a velocity, s is a cross-sectional area. So similarly here, similar to that equation, in a three-dimensional way, we will be deriving this continuity equation. That is m dot is equal to rho us is a one-dimensional. Here, using all the three coordinates, spatial coordinate system, we will be deriving this equation, continuity equation. Then there are two types of diffusions. One is a molecular diffusion, another one is a eddy diffusion. So among them, molecular diffusion, we will be paying a special emphasis on this molecular diffusion. So in the molecular diffusion cases, there are two cases. Okay, there are two fluid phase cases. One is a gas phase and next one is a liquid phase. In gas phase, how the diffusion will takes place. Okay, there are two phenomena in gas phase. One is a through non-diffusing B. What is the meaning of that one? We will discuss, don't worry. Then next one is equimolar counter diffusion. And among the liquid phase also, there are two cases, similar cases, A through non-diffusing B and also equimolar counter diffusion. Okay, this all combined together, we will say the four cases. How it is four cases? A through non-diffusing B in gas and equimolar counter diffusion in gas phase. Similarly, A through non-diffusing B in liquid phase and equimolar counter diffusion in liquid phase. So like this, the 4 cases will be there. Among these 4 cases, if you observe the previous question papers, among these 4 cases, one case is compulsory. They are giving one case compulsorily. They are giving one case. Okay, derivation is somewhat similar for each cases. So you have to know how to derive that particular equation. Okay, so better to concentrate everything keenly. The next topic will be mass transfer in turbulent and laminar flow. Okay, in the turbulent flows, what happens generally? We will be incorporating some mass transfer coefficients. Okay, that coefficients, if you know this 4 cases clearly, then the mass transfer coefficient evaluation is very easy. Okay, just simply this formula is defined in separate form. Okay, it's defined in separate form. That is nothing but this section entirely. If you know this 4 different derivations, then it is very easy to deal with this topic, mass transfer in turbulent flow and laminar flow. The next topic is interface mass transfer. Okay, the mass has to transform from one phase to another phase. For example, from gas phase to liquid phase is getting transferred, or we can take liquid phase to gas phase, or some solid phase to some gas phase. Whatever the phase it may be, whenever it is transforming from one phase to another phase, so in between there will be some distinct layer. For example, gas and liquid you take. In the gas and liquid, there will be some interface. Okay, interface. How in the interface the mass transfer is taking place. Okay, from the bulk to interface and interface to the other interface of the other phase, then other interface of the other phase to the bulk of that other phase. So how it is taking place? To define that one, or to define how the mass transfer is taking place, there are many theories out there. One is a film theory, next one is a penetration theory and surface renewal theory. So in the among the film theory, one other theory is also there, that is two film theory. So one is a gas phase, one is a liquid phase, like this. So all these theories we will be discussing. Then last topic of this unit is estimation of mass transfer coefficient using weighted wall tower. So weighted wall tower will be there. So that is the experimental setup. We will be dealing more with this weighted wall tower to estimate mass transfer coefficient experimentally. So these are the contents which are there in unit 1. So then we will study what is a mass transfer first. Okay, generally we are discussing mass transfer. This course itself is a title of this course itself is a mass transfer operations. So what is a mass transfer? So the transfer or migration of species or material or matter from higher concentration region to lower concentration region, or from one phase to the another phase system, or without phase change or with phase change. Everything is nothing but transfer of mass or mass transfer. So mass is getting transformed from one location to another location, or one concentration level to other concentration level, or one phase to another phase, whatever it may be. That is entirely the process is called mass transfer operation or mass transfer simply. So usually the mass transfer in the general sense, it will be takes place from higher concentration region to lower concentration region. Similarly, heat transfer also. Whenever two different temperature bodies are brought into together, okay, so the temperature, the body which is having a higher temperature will be exchanging heat with the body which is having a lower temperature. So the heat transfer will also takes place from higher temperature region to lower temperature region. Similar phenomena also can be observed in the mass transfer, which is the mass transfer can be taking place from only from higher concentration region to lower concentration region naturally. Okay, then it is very complex phenomena. Mass transfer operations is very complex phenomena, occurs almost in all unit operations. Okay, you know what is unit operation and what is unit processes. You might have studied in this CPP course, chemical process principles. So unit operations are nothing but in which only physical changes will be occurring. Okay, there is a mass transfer with chemical reactions are also there. That will be carried out as a denoted as a unit processes. But that is very critical to evaluate mass transfer with reaction. Okay, so we are not concentrating on that one for your limited syllabus in your UG course. So mass transfer with chemical reaction is not there. Okay, only when you do some specialized courses or some advanced courses in the PG, okay, then only you can see that type of complex processes. But according to your syllabus, only it is enough to learn mass transfer without chemical reaction. So without chemical reaction means only unit operations are enough. Then occurs the mass transfer operation occurs through different mechanisms such as molecular diffusion, then convective or bulk flow and turbulent mixing. So whatever it may be, the mass transfer will be taking place from one concentration region to other concentration region. For example, in this, if you see, there are two different types of molecules. One is a red color. One molecule type is a red color type of molecule. Another molecule is a green type of molecule. So whenever they are separated using some porous plug, okay, some plug or some valve is put in between the two cells. Okay, when you remove, okay, when you just open that plug or when you open the tap, what happens? The interchange of mass will be taking place depending on their interaction with other, depending on their traveling tendency from one region to other region. So the red molecules will be traveling from this higher concentration region to lower concentration region, and green molecules which is having a higher concentration here will be traveling from higher concentration region to lower concentration region as shown in this figure. So further, if you allow until the equilibrium, so molecules will be reaching a some equilibrium point. Okay, if you allow a maximum period of time, it will be reaching a equilibrium point of time. So this is the phenomena which is taking place. It is a simple example how the molecules are getting transformed from one region to another region, from one cell to another cell. Okay, how they are traveling from this cell to that cell. So that is phenomena is called, that phenomena is called as a diffusion. Okay, the traveling of this molecule from this one cell to another cell, or traveling of this red molecules to green molecule side. So that phenomena taking place is called as a diffusion. So how this diffusion will be happening? So the transference of a component in a mixture from a region where its concentration is high, nothing but higher concentration region, to a region where the concentration is low, nothing but the lower concentration region. The transfers of components from higher concentration region to lower concentration region is called as a diffusion. So the mass transfer process can take place in a gas or vapor or in a liquid, and it can result from a random velocities of the molecules. So due to its velocities only, it is getting travel from one cell to another cell. So that random movement or random velocities is called as a molecular diffusion, or from a circular or eddy currents present in a turbulent fluid. That is called as a eddy diffusion. There are two types of diffusion. One is due to normal movement or a general random movement is called as a molecular diffusion, or whenever you are putting some agitation here, okay, whenever you are pushing that molecule to travel forcibly to travel, so then some eddy currents will be produced. That eddy currents will be giving you this type of diffusion, that is called as a eddy diffusion. So there are two types of diffusion. One is molecular diffusion, another one is a eddy diffusion. Molecular diffusion is caused due to random velocities, random movement of molecules. Then eddy diffusion is caused due to circulating or eddy currents present especially in the turbulent fluids. Okay, similarly in the fluid mechanics, you have seen that one, turbulent flow and laminar flow. The same type of phenomena, this is also in terms of mass transfer. Okay. Any doubts until here? The diffusion, you understood the concept? The diffusion.
Yes, sir.
Okay, then
Excuse me,
next. Yes, yes.
sir. What is mean by eddy currents?
Eddy currents means, first of all, see, in the fluid mechanics example, I will tell you. So, for example, a fluid is traveling like this. Fluid is there inside the pipeline. So inside the pipeline, fluid has to travel. Okay, fluid inlet this is. And this is fluid outlet. Okay, when this traveling, I am taking only this region now. Okay, that region means, see, this is only fluid. When it is straightly moving as a placards. Okay, it is moving as a placards without interacting with each other. Just simply, it is just moving like this in a card, in a placards manner. So this is called, whatever you are calling in this fluid mechanics course, that is laminar flow. Without interacting with each other, it is just in a stream way it is moving. Similarly, for the turbulent flow, what happens whenever fluid is traveling as in the form of turbulent flow, what happens? It will be just traveling like this. So one layer will be counter connected to each other. So it will be mingling with each other like this. So then a packet, small packets like of interactions will be formed here. So this is what we are denoting there, that is turbulent flow, when there is a interaction between the layers of the fluid. So that is called as a turbulent flow. When there is no interaction between layers of the fluid, so that is called as a laminar flow. Similarly, here also, when there is a two cells are there, these two cells are there. Okay, I am not putting any this one plug here, plug or this. This is one cell and this is another cell. This is another cell. Okay, among here there are red type of molecules. Okay, red type means it is not a type, only to denote the color convenience. Okay, to know more about the molecules are taken as a red color. So apart from that, no importance of that one. Okay, these are the green molecules. Whenever you are removing the plug, okay, whenever you are opening the valve, what happens? This has to transfer or travel from this region, this cell to, for example, let us say this is cell 2. This is some cell 1 or vessel 1 or vessel 2. Okay, whenever they are traveling, whenever you are opening this one, so this red molecules will be traveling from this direction to, okay, from left direction to right direction, whereas this cell molecules, green molecules, will be traveling from this direction to this direction. Whenever they are traveling, if these red molecules are interacting like this, these red molecules, these are traveling like this, and green molecules are traveling like this. Okay, whenever these are interacting like this, small packets will be formed due to their interaction. Okay, not just the abrasion, due to the interaction, a small packet like this, agglomerates will be formed. So these are called eddies. Okay, as a packets they will be moving together. So these are called eddies. Whenever in the normal flow, these are, for example, these are green molecules and these are red molecules. Whenever, for example, only one molecule I am taking, this one molecule is traveling like this. Okay, with just a small interaction with each other, it is traveling like this. So this is called as a normal random motion. Okay, it is not moving like a packets. Okay, combinedly they are not moving, individually independent from each other they are moving. So that type of flow is called as a eddy diffusion, eddy type of flow, or we can say that is eddy currents, we can say this type of flow. And these are just a random motion without being an independent molecule, they are moving each other. Okay, one molecule is moving like this, and similarly for this case also this is moving like this. Okay, this is called eddies whenever they are moving in a packet form, whenever they are moving in a normal form. So that motion is called as a random motion. Okay. Is that clear?
Okay. Yes, sir.
Yeah, thank you. Yeah, then generally this molecular diffusion is often simply referred to as a diffusion. Okay, molecular diffusion is not a separate one. Diffusion itself means a molecular diffusion. Okay, molecular diffusion is generally referred to as a simply a diffusion, and it is caused due to the thermal motion of particles. Okay, thermal motion means due to a random, okay, normal motion, it is just caused in everything like a gas or liquid at temperatures above absolute zero. Okay, above absolute zero only. Absolute zero temperature means it's a 0 degree centigrades. Okay, absolute zero means 0 degree Kelvin. Absolute temperature means Kelvin, Kelvin denotion, that one. So above 0 degree Kelvin, it will be having this molecular diffusion will be having. Then the rate of this movement, okay, whenever the molecules are moving from one side to another side, the rate of this movement is normally a function of temperature, viscosity of the fluid, and also the size of the particle. Okay, whenever these molecules are moving, whenever these molecules are moving from one side to another side, so it will be dependent on its size of the molecule and temperature. what is the temperature inside. If the temperature is there, it will increase the kinetic energy of the particles. Okay, kinetic energy, you know, kinetic energy will be increased if the temperature is very high. If the kinetic energy is very high, it will be moving with a fast motion. Very fast motion can be observed. So it may be turned from laminar to turbulent due to the increase in the temperature. So the rate of the movement of molecules from one region or one cell to another cell is a function of temperature, size of the molecule, and also viscosity of the molecules or particles viscosity, or in the medium viscosity. Everything is a function of the rate of movement is a function of temperature, viscosity, and size of the molecule. So diffusion is nothing but the net flux or net movement of molecules from a region of higher concentration to the region of lower concentration is called as a diffusion. In other way, when you define the region, the diffusion is nothing but the net flux or net movement. Flux, what is flux we will define later. Net flux or net movement of molecule from higher concentration region to, so this is higher concentration region for the red molecules only. So here there is no red molecules. So this is lower concentration region for the red molecules. So they are traveling from higher concentration region to lower concentration region. Similarly, for green molecules, this is higher concentration region. Why? Because they are present in a maximum number. Then this cell is a low concentration region for the this green molecules. So they will be moving in this direction, and they will be red molecules are moving in this direction. So diffusion is nothing but a net flux or a movement from a higher concentration region to lower concentration region. So typically a molecular diffusion is defined as a mathematically, this diffusion can be defined using the fixed first law of diffusion. Okay, fixed first law of diffusion. Using the fixed first law of diffusion, we will be defining that one. Now you see molecules are moving from this region to this region, or this region to this region. So what is the flux? Okay, flux is nothing but this one. Yeah, moles. Okay, for example, these are having some moles. Okay, usually the gas phase will be concentrations will be measured in moles per meter cube, or moles per in concentrations they will be measured. So moles of molecules, okay, flux is nothing but FLUX, this is. So flux is nothing but moles of molecules. Okay, for example, only red example, green example, let us take moles of green molecules or green particles traveling from one region, higher concentration region, to lower concentration region per unit surface area. What is the area to travel this one? That is measured in meter square. That is area, okay, moles per meter. Okay, per unit time. Okay, per unit time is called as a flux. So flux will be having units of, so moles of green molecules travel. So it will be measured in moles. Moles mean moles only. Moles per unit area means area is measured in meter square. Then time is measured in seconds. So flux will be having a units of moles per meter square second. This is nothing but flux is nothing but the movement of molecules. Whenever there is a movement of molecule from one region to another region, or one cell to another cell, or one vessel to another vessel, that molecules movement with respect to moles in their moles per unit area, okay, to available to travel the into time per unit time is called as a flux. So this is the general quantifying of that molecules. Molecules, moles of molecule, that molecules traveling from one region to another region per unit time per unit area is called as a flux. So this is the definition of flux. Generally, the molecular diffusion is defined with respect to this flux only, with respect to fixed first law of diffusion. So fixed first law of diffusion is the basic governing equation. Basic governing equation in the mass transfer operation. So this is very, very, very important. Without knowing fixed first law of diffusion, you cannot understand anything. Okay. Similarly, in the heat transfer, okay, I am just analyzing, framing an analogy between fluid mechanics, heat transfer, and mass transfer. These are all the transportation processes only. Whether fluid mechanics, heat transfer or mass transfer, all these are the transportation process. In fluid mechanics, fluid will be transporting from one region to another region. In heat transfer, the heat is getting transformed from one region to another region or one body to another body. In mass transfer, mass is getting transformed from one body to one region to another region. So in heat transfer, the basic governing equation is a Fourier's law of heat conduction is the governing equation there. Then in fluid mechanics, that is Newton's law. Newton's law of viscosity. Okay, then what is this Fourier's law? Before going to, I hope this in the heat transfer, they have covered this one, fluid mechanics, we are teaching this course. So this Fourier's law is nothing but flux. Okay, heat transfer flux. Q is heat transfer flux is directly proportional to minus negative sign dt by dx or dt. This is dx only, yeah. dt by dx. Fourier's law of heat conduction, this one, in which the proportionality constant, this proportionality constant is nothing but conductivity, K, thermal conductivity. So minus sign will be there like this. So dt by dt. This minus sign signifies that heat transfer will take place from high temperature region to low temperature region. So this minus sign will signify. This is called as a Fourier's law of heat conduction. Similarly, in the fluid mechanics, so Newton's law of viscosity will be there. That Newton's law of viscosity is nothing but stress is directly proportional to strain. Strain is nothing but change in velocity with respect to change in the direction with respect to the spatial coordinates du by dx. So this also minus sign signifies that the movement of that velocity is from higher velocity region to lower velocity region. So the direction is changing. The direction from one region to another region is changing, that one. So in which the proportionality constant is, we are denoting with viscosity mu. Minus is there, then du by dx. So this we are calling as a stress and this we are calling as a strain or change in velocity with respect to change in spatial coordinate. Then this mu is a viscosity. Then here it is heat transfer flux. Heat transfer flux. Then this is gradient. Okay, heat transfer gradient. So this also we can write as strain or we can write as velocity gradient. Velocity gradient. Then this is heat transfer gradient or change in temperature with respect to spatial coordinate. In this one, this K is nothing but thermal conductivity. Thermal conductivity. Similarly, if you know these equations, you can easily define the fixed first law of diffusion. How we can define the fixed first law of diffusion? That is JA. So in which in the mass transfer flux is denoted by JA or NA. Okay, NA or JA. So what is the meaning of this JA and NA? We will be seeing later. Okay, for the time being, just remember JA is the flux. So flux is directly proportional to concentration gradient dou Ca by dou X. Okay, dou Ca by dou X, or if you are measuring in the direction of Y, so it is dou Y, or in the direction of Z, it is dou Z. Okay, whatever the direction, whatever the spatial coordinates. Okay, spatial coordinates are this one. X, Y, Z. If you are measuring the flux with respect to this direction, you can use the dou X. If you are measuring in Z direction, you can use dou Z. If you are measuring in Y direction, you can use dou Y. Whatever it may be, just remember the fixed first law of diffusion is nothing but JA. So here minus is there. This minus will also signifies the concentration movement is from higher concentration region to lower concentration region. See what is the similarity between all these equations, all these operations, whether fluid mechanics, heat transfer or mass transfer, whatever it may be, every operation is a transport operation only. Okay, the similarities they are very similar. So all the basic governing equations, see, flux is directly proportional to the gradient. Here also this is a concentration gradient. concentration gradient. Similarly, in the heat transfer, it is a heat transfer gradient. In the fluid mechanics, it is a this velocity gradient, this one. Here it is mass transfer gradient or concentration gradient. So just directly JA is a flux. So this one is a flux is directly proportional to the negative gradient dou Ca by dou X. So this is a concentration gradient. This is a flux. Then in this also, what is the proportionality constant? Proportionality constant is nothing but here is diffusivity, DAB or diffusion coefficient we can say. So minus is there from the previous equation, dou Ca by dou X. So this is the fixed first law of diffusion. JA is equal to dou Ca minus DAB dou Ca by dou Z or dou Ca by dou X. So this JA is mass transfer flux. So whose units are mole per meter square second. Then DAB is diffusivity, or simply we can say diffusion coefficient. Diffusion coefficient. Then Ca units, we will derive units so that you can remember easily. So concentration, it is also a general term. So this is concentration of species A. Species A. Okay, if you want to write the same equation for species B, how do you write? JA is equal to minus DBA. Now JB is equal to, for B, component B, if you want to write, that will be JB is equal to minus DBA into dou CB by dou X. Okay, why? Because we are writing the flux equation, fixed first law of diffusion, for the component B. Okay, this is for component A. So what is the significance of this component A, B, C? I will define now. So this is concentration of species A. So means concentration units we already know. That is nothing but mole per liter or mole per meter cube, whatever it may be. Mole per liter. So this is the concentration unit. So this is nothing but distance. Okay, distance is measured in meters. So what is this distance? See, I am once again drawing this figure. Okay, two cells are there. For example, this molecule is moving from this cell to this cell. So the distance traveled by the molecule is nothing but this X. Okay, the concentration of molecules, okay, from this region to this region, how much it has been exchanged. So that is Ca, concentration. Then the what is the velocity, okay, by at which velocity, random movement, how it is happening due to the diffusivity. So that diffusivity is called as dA to B. So this is called as dA to B or DAB. Simply we can call DAB or dA to B. That originally is known as dA to B. So this signifies the direction of movement. Okay, A is getting transformed to B. So that is, so simply we can say DAB. The overall movement, okay, the overall movement of this one is called as a JA. So measured of this process, entirely the mass transfer process, is called as a flux or JA. Simply we can say JA or flux. So from this one, can we define the equation of DAB? JA is equal to minus DAB dou Ca by dou X. So JA will have a units of mole per meter square second is equal to DAB for the time being. Neglect this minus. Then Ca units we already know. What is the Ca units? Which is mole per meter cube. Then we know X units, the direction or the distance, which is meter. So then what happened? This will be going this side. So this will be mole per meter square second is equal to DAB mole per meter power 4. This is. Then this will be going to this side, or we can call this, cancel out this mole and mole. Then the left out terms will be this meter power 4 will be moving to the numerator of this LHS side. So meter power 4 meter square into second is equal to DAB. So this is cancelled. So then finally the left out terms are DAB is equal to meter square is left in the numerator, meter square per second. So then the units of DAB is nothing but meter square per second. So we can write here the units of DAB or diffusivity coefficient or diffusivity is nothing but meter square per second. So the flux equation for other components, how we can write? Okay, for example, in a system, okay, in a closed system or
Sir,
whatever the system. Yes, yes.
sir, paina minus.
Okay, minus ఇది యూనిట్సే కదా జస్ట్ సో మైనస్ అవసరం లేదు యూనిట్స్ కి మైనస్ ఎక్కడ ఉంటుంది అర్థమైందమ్మా
ఓకే సార్
యూనిట్స్ కి మైనస్ ఉండవు మనం ఇది ఈక్వేషన్ లో రాసేటప్పుడే మైనస్ రాస్తాం క్యాలిక్యులేషన్ లో కానీ యూనిట్స్ డెరైవ్ చేసేటప్పుడు మైనస్ అవసరం లేదు మైనస్ మీటర్ ఆర్ మైనస్ మీటర్ స్క్వేర్ అవి సిగ్నిఫైస్ ఏం చేస్తాయి నెగిటివ్ యూనిట్స్ ఉండవు ఎప్పుడు ఓకే
ఓకే సార్
అర్థం కాకపోతే అడగండి ఓకే దెన్ ఇఫ్ యూ కన్సిడర్ దిస్ యాజ్ ఎ సిస్టమ్ ఓకే ఇన్ వన్ సిస్టమ్ దేర్ ఆర్ మెనీ స్పీషీస్ okay, for example, this molecules black molecules are A and this green molecules are B. Then next one is this one, this blue molecules are some C. Okay, then this yellow molecules are some D. Okay, there are many number of species in a system, let us say that one. So if you want to calculate the flux of this molecules, black molecules, then this is denoted by A. Then how the fixed first law of diffusion you will write? JA is equal to
minus
DAB dou CA by dou X or dou Y or dou Z. Then for only this B, how do you write? For B, we can write as JB is equal to minus, just change the direction. Just change the direction. Now the importance will be there for B. DBA, for example, it is moving towards this one. Then DBA dou CB per dou X. Then for example, if you want to write for the blue molecules, C molecules, then how do you apply the fixed first law of diffusion? That is JC is equal to minus DC. Let us say the movement is from C to A. Then this is DCA. If it is from C to B, then in place of this we can write minus DCB. Okay, C to B. If the movement is from C to B, we have to take consideration C and B. If the movement is from C to A, then we have to write C to A, this DCA. So for the time being, let's say from C to A it is moving. That is DCA dou CC, concentration of molecule C divided by dou X. Then next, if you want to write for the yellow molecules or D molecules, then you can write for this one is flux of D is equal to minus D. So now for, let us say the movement is from D to B, then we have to write D to B, that is DDB into dou CD by dou X. So this is how you have to apply fixed first law of diffusion. Don't worry, you don't have to do all this one. Okay, one component is enough. Why? Because for your UG syllabus, only we are assuming that for your syllabus, only they have given two component system. This is only for your syllabus. Okay, when you go for the PG or something else, there will be n number of components, mixture of component, multi-component system. So that is not there for your syllabus. You don't have to worry about that one. Only two component system will be there. Two component system means only two components will be involved. Maximum the two components we will be denoting using A and B. Okay, you can give any name, C and D also you can give. But it is very convenient to define A and B. Only molecule A and molecule B will be there. So you maximum, okay, maximum for your syllabus, you will be using JA, JB, and DAB and DBA, then dose CA or just CA and CB. So this is only you are using plus, okay, only one dimensional. Okay, for your assumption, that is only one dimensional. So what is the meaning of this one dimensional? Meaning of two component system is A and B. Only two components are involved. So meaning of one dimensional means, okay, this is X, this is Y, and this is Z. So you have to neglect this direction and this direction, or you neglect this one. Okay, X, Y, and Z. You neglect X and Z. Consider only Y, only one dimensional. Or you can do another thing also. X, Y, and Z. In this one, now you can neglect X and Y and only consider Z. In the first case, you consider X. In the second case, you consider Y. In the third case, you consider Z. Okay, only one thing is valid. These are all known as one dimensional. Okay, not this is 1D picture only, not 2D or 3D. Okay, 1D for your syllabus, only one dimensional, that too only two component system. Okay, that is the assumption for your whole syllabus. Okay, you need not to worry about this multi-component systems. Okay, in our BTech, during BTech chemical engineering, in the though that is UG, we have a multi-component system also. We have to deal with many components, not only two components. But for your syllabus, BSc syllabus, it is enough to have only two component system. Only two components are there. You need not to bother about all the remaining components. Okay, I hope this you understood clear. It is clear. Everybody.
Yes, sir.
Yes, sir.
Yeah. Okay. If you have any doubts, please don't hesitate to stop me anywhere. These concepts are very, very, very important. Repeatedly, I'm stressing about this one. These concepts are very, very important. Okay. Now you understood what is diffusion. Okay. How the mass transfer is taking place. What is the importance of a diffusion now? What are their units? What is the fixed first law of diffusion? Everything you have seen. So where this application of molecular diffusion, now we studied molecular diffusion, where will be the application of this diffusion, molecular diffusion? So especially this molecular diffusion is useful in chemical reactor designs. Okay, in the next sem you might be seeing this chemical reaction engineering. Okay, in designing that reactors, okay, we will be using these principles of diffusion, and in the design of catalyst also. Okay, catalyst, you might be aware of the catalyst. What is a catalyst? For example, if there is a reaction A plus B gives rise to C plus D. Okay, how these two are the reactants. These two are the products. Okay, to happen this reaction spontaneously. Spontaneous reaction means nothing but it will happen naturally. Okay, naturally happening reactions are known as spontaneous reaction. If they are happening spontaneously means we need not to add any external thing. A plus B, just mix this one, just mix this one. So after reaction, they will be forming directly C plus D. But in this universe, okay, in this any industry, what happens? All the reactions are not at all spontaneous. Okay, even our water formation, okay, H2O is not a spontaneous one. Okay, to accelerate that one, spontaneous to some extent, but to form that normal water from the hydrogen plus oxygen, H2O. H2O, what is the meaning of H2O? Hydrogen plus oxygen. To form it a normal it is spontaneous somewhat, but to form it in a normal condition, so it will take years. But when you add some catalyst, okay, some external aid to decrease the activation energy, then it will be forming within a minutes or within a seconds also it can form. To accelerate the reaction or to decelerate the reaction, to decrease or increase the speed of the reaction, we will add one type of component that is called as a catalyst. Okay, in designing this catalyst can be anything, homogeneous or heterogeneous. Okay, you need not to bother about this terminology. Just for simply I am saying homogeneous means same phase. If the reactants and products all are in the same phases along with the catalyst, so that systems are called homogeneous system. If reactants and products are at different phases, For example, this is liquid phase, this is gas phase, and catalyst is in some gas phase. Then what happens? Phase is different here. So that type of systems are called heterogeneous systems. If this is also liquid, this is also liquid, then what happens? Both phases are same. That type of systems are called homogeneous systems. So there are various types of catalysts are there, whatever it may be. In designing the catalyst, this diffusion principles of very much useful. These are the basic principle to design the any type of catalyst. Okay, then in the semiconductor industry, in this electronics industry, in the manufacture of semiconductors, doping will be there. Okay, doping means some metal will be doped. Okay, for example, some chip preparation. Okay, some computer chips preparation. Some doping phenomena will be involved. In the doping also, this diffusion is very important. Okay, for example, if you want to prepare some motherboard, computer motherboard. Okay, on the motherboard, if you open some TV also, in the television also, there will be the motherboard. In the motherboard, there will be some black chip like this, some red chip will be like this, some green chip will be like this. So there will be a connection, small anodic connections will be there like this. So how this all will be manufactured? Okay, how these chips are something will be deposited onto this big chip or big motherboard. So due to the diffusion only, it is possible to deposit there everything. Okay, not only in the chemical industry, in the electronic industry, any industry, the phenomena taking place is this one, which is a diffusion. Okay, molecular diffusion. So then next one is the eddy diffusion. Eddy diffusion, we know that it is due to the packets movement, okay, or due to the eddy currents. Okay, it is the mixing. Eddy diffusion is nothing but it is the mixing that is caused by eddies that can vary in size from smaller macro scale, micromolecular scale to subtropical scale. Okay, the eddies can be anything. Okay, for example, I'm showing one barrier. So for example, initially there is some barrier. Okay, there are molecules here. Okay, this is a empty. Then after eddy diffusion, what happens? Same barrier will be there once again. So this barrier, now you have lifted this barrier. Then what happens? The movement will be, these molecules will be moving like this. Okay, this like this. And whenever it is moving like this, a small eddy packets or eddy currents will be formed. So this is a eddy diffusion. So what is the importance of eddy diffusion? So where are this eddy diffusion will be used to accelerate the any type of diffusion process? Eddy diffusions will be used. And the normal conditions, molecular diffusion is enough. But to accelerate anything, so we have to use the eddy diffusion. Like in the this one, chemical reactions in jet diffusion or in the jet planes. Okay, in the jet planes, what happens? Some oxidizer has to be mixed with some fuel. Oxidizer and fuel will be mixed. Okay, for example, let us see. This is some rocket or some jet. Okay, in the rocket, you might be seeing something is burning like this. Okay, some combustion of gases will be releasing and this will be flying like this. So how this is possible? Inside this one, there will be some fuel tank. Okay, there will be some fuel tank. That fuel can be anything, solid propellant. Okay, that is called as a propellant or liquid propellant. This propellant, and apart from this fuel tank, there will be some oxidizer. Why means anything to burn. Okay, anything to burn, we need oxygen. Okay, for example, in the fire retardants. Okay, fire retardants, CO2 will be there. You might be observing some CO2 cylinders where the firefighters or some fire fighting elements are there. Why they will keep CO2? When you add CO2 to the surrounding atmosphere, obviously the oxygen supply will be cut down. When there is no oxygen supply, that will not burn. Okay, anything will not be burned. Okay, you will be throwing some sand whenever something is burning. Okay, unrequired burning is there. You will be just throwing some sand. What is the role of that sand? It will cut the supply of oxygen to the air through that particular fire. If the fire is there, if you supply oxygen there, then the fire will be increased furthermore. So to combust any type of fuel, there will be need of an oxidizer. Okay, in the rocket fuels, this is especially useful. So this has to mix. Fuel will be mixed with oxidizer. Then only the combustion can happen. In the jet fuel combustion chambers also, this eddy diffusion to diffuse it fast, this will be used. Then many combustion burners, okay, in the burners, okay, in this butcher shop, okay, the best example is the butcher shop. Okay, if there is a butcher shop or the chicken shop, you can see. Okay, earlier, nowadays maybe they are not doing. If there is a chicken, okay, if there is some chicken like this, okay, I have not drawing accurately. So earlier days, what they have to use, the chicken hair will be there, no, this one like this hair, they will be using some burner to burn the chicken. Burner will be there. So in this one, some fuel will be added along with some oxygen supply will also be there. So in this one, there is a need to vigorously mix oxygen plus fuel. Then only the burner will be burning at high rates. Okay, then only this chicken hair will be entirely burnt. Burnt chicken. Okay, nowadays also this one country chicken. In the preparation of this country chicken also, this is using burner. Okay, you can observe in any chicken shop this phenomena. There is a requirement for eddy diffusion. Then atmospheric diffusion and this pollution dispersant from the atmosphere, everything will be the example for this eddy diffusion. Okay, generally everything will be taking place in the molecular diffusion only. Whenever there is a special requirement, then only this eddy diffusions will be used, in which the the molecules will be moving in a using the eddy currents or the some small packet like of things. Okay, is it clear until now?
Yes, sir.
Yes,
Okay,
sir.
then tomorrow, I think in CPP course, you might be, you have heard this one, universal gas constant, R value. Do
Yes,
you know
sir.
what is this R value?
9.8.
9.8 units. Okay, R value is equal to 0.0821 atmoliter per mole degree Kelvin. R value is equal to 8.314. This will be units Pascal meter cube per mole degree Kelvin. R value is equal to something 62.7. Okay, I don't remember exactly the units here. mmHg, okay, something like this, mole Kelvin, okay, mmHg liter something, okay. R value is equal to 8314, okay, kilopascal meter cube per kilomole mole degree Kelvin, like this it will be there. So all this, there are many R values are there. So the first basic R value is this one, 0.0821 atmoliter per mole degree Kelvin. I don't know whether in the CPP course you have seen how to obtain this basic R value. Then you can, if you know this R value, using the unit conversion, you can get all the other values. Okay, whatever the value is there, all the other values depending on whatever the requirement of units, we can convert. To derive this one, there is a basic small concept I would like to tell. Have this. This topic has been covered in CPP, how to derive this R value, PV is equal to nRT using the STP and NTP conditions, how to derive the R value. Have you know this one? Anybody? Okay, I hope
Yes,
nobody
sir.
covered that one. You know that one? How to
Yes,
derive
sir.
R
We
value?
hear. We hear,
Yes,
but
sir.
not about that.
Okay, then tomorrow once again I will derive that one, R value, how to derive and how to convert from one conversion units to another conversion units. Just please pay attention. Okay, then thank you for listening. Any
Thank you, sir.
doubts? Any
No,
doubts?
sir.
No, no.
No, sir.
Okay.
Thank you.